I don't know. I can see it. Sorry. Okay, thank you. All right. Maybe I'll go upstairs and see whether there are people, especially if I need them. Change your color.
So like it's not like a computer.
That's funny. Just the projector. Okay, let's get started. So, yeah, welcome to the afternoon session. So today we're very happy to have the first talk of the afternoon, and just gonna have some joint work with Jennifer with Nicole, and the title is Fixing Time of Open Quantum System by
Thank you very much for the introduction, and I really appreciate the appreciation. And my chair supposed to be just came. Okay. Well, thank you everyone for coming to my talk today. So what I plan to talk about is about the mixing time of open quantum system. Specifically, I'm going to dive into the idea of the so-called hypercoercivity. I will talk a little bit about what it actually means. And as you can see, this is joint work with Jianfeng Lu, who is a co-organizer of this event, sitting in the audience, and also Yu Tong sitting in the audience. So as you can see, all the three of us are in Duke, but actually this project didn't start until all of us were actually at UCLA, at the LA area. So sometimes it's good for us to travel around, sometimes new idea can come along. So here is the outline. First of all, I will discuss what is a mixing time. I will just define the definition of the problem because we have already seen various reasons why, why we want to consider this problem. So I will discuss a little bit what is mixing time, what are the state of art, what are the relevant tools we use to estimate mixing time, and then propose an open question. After that, I will discuss this idea of hypercoercivity, and then I will discuss the results of our work, especially the statement of how we understand it. And then I talk about some of the applications. Okay, so let's get started. I'm going to start by talking about Lindbladian equations. And we have already seen this equations a zillion times inside of this workshop, which is the topic of the workshop. So I will not discuss like what is motivation, how we derive it, but rather I will just say that inside of my talk today, I will mainly focus on the Heisenberg picture. While I'm looking at the observables that are time evolved, and we have a Hamiltonian part, this curly A stands for the Hamiltonian part. And then I also have a dissipative part that is governed by all of these jump operators. So this D, curly D is the dissipative part. And as we have seen in many of the previous talks, there's also a duality representation in the Schrödinger picture where we can look at the time evolved state. And this is the corresponding picture. So the two pictures are exactly equivalent under the duality in the regular Hilbert-Schmidt inner product. So throughout my talk, whenever I see L, I mean the Heisenberg picture, and all of these are Heisenberg pictures. So when I say star, this means the corresponding Schrödinger's picture. So now what is mixing time? I just want to say the definition of mixing time that we want to study is how fast does the system approach to its equilibrium? Otherwise, how fast does it thermalize? Before diving into the concrete definition of mixing time, I just want to discuss a little bit of why do we care. As you are in this conference, you already know why we should care, but I think it doesn't matter. I just briefly go through it again. So dated back to 2009 by these amazing folks, they have shown that dissipative quantum dynamics is actually universal, can be used to do universal quantum computation. And later, they find this pretty useful in terms of quantum field theory simulation in their later papers. And then we do understand there is a surge inside of this field. Greater advances has been made since last year. At least some of these really significant advances in the field. For example, we have seen Lindbladian dynamics can be used to prepare thermal states and ground state preparation, local minimum, which will be the next talk, and quantum control, which we have already heard about, and also sometimes some classical optimization. So the point is that many of these algorithms are actually talking about Lindbladian equations. Specifically, if you look at some of the formulations, say if you talk about ground state preparation or classical optimization, the formulation is that you want to formulate your Lindblad equation in the form so that the thermal states is the actual solution you want in the end of the day. So you can imagine, then you use a quantum algorithm to solve it. The mixing time will come into the complexity estimate or the cost estimate, at least in a polynomial fashion. So you know how long you need to simulate those equations. That's why mixing time is a really important feature, not just because it's obvious physical meanings, but also because the algorithmic applications. What I find particularly amazing for this workshop is that for all these recent developments, for each of this significant work, at least one of the authors is actually in the audience. So this is where our workshop is really great. So now I just want to define what is the mixing time that I'm going to talk about. So this has already defined by other talks. So I'm going to look at the Shutter-1 norm or the trace norm, whichever way you prefer. And then I'm looking at the Schrodinger's picture, and I want to show that its evolution up to thermal state is bounded by a certain epsilon. And this is the notion of mixing time that I'm going to use. Apparently, this is a quantum information, which is our target question. However, we do understand that this problem have various different names, a quantum Markov semigroup. Just as Nathan said, sometimes if its name already suggests you what you want to do, that's great. So we do understand that Markov semigroup, then there is definitely a probability viewpoint. For example, you can utilize the tools in ergodicity theory and detail balance, which is very important, and we have seen a great deal about that. At the same time, this is really a differential equation. So correspondingly, people can also think about from a differential equation viewpoint, correspondingly dynamical system where when we talk about the global equilibrium, we will talk about maybe some energy estimates or the output of energy functionals. So our approach is more aligned on the output functional approach, which I will show you soon. So now it's time to just revisit a little bit about the existing works, amazing of the advances in this field, how to estimate the mixing time. So I would say this is the typical route that one will take. First of all, you have a Hamiltonian. First of all, you have a Lindbladian of your interest. And the first thing you do is you choose your favorite inner product. Well, it can be GNS, can be KMS, can be any of the other interpolation. And then you want to first check that your Lindbladian is actually detail balanced. This will ensure that the eigenvalues, the spectrum of the Lindbladians are actually real. So it makes sense for us to talk about the spectral gap notation. So this would be the first thing that you want to check. If not, you can imagine the spectrum is not guaranteed to be real. So instead of the full Lindbladian, people can talk about the symmetrization of the Lindbladian so that it satisfies the detail balance. In other words, you look at the Hermitian part of the Lindbladian. If this is satisfied, great. Then the next task we need to do is to estimate the lower bounds of the spectral gap. Because all of the spectrum now is real, so we can just talk about what is the spectral gap in a very well-defined way, so that we can estimate the lower bounds of the spectrum. There is this amazing set of works along this line. And then if we say the spectral gap is G, then we can easily get exponential decay. We will immediately get that this is a Heisenberg picture where G exactly governs the decay rate. And then we can just simply use the duality argument. The Heisenberg picture and Schrodinger picture follows the duality argument and simply get a mixing time estimate. The take-away message would then be, especially for quantum algorithmic applications, is that if the mixing the gap is polynomial, correspondingly we will have a polynomial mixing time, which will mean the quantum algorithm is very efficient. There is another line of work, for example, for this, if we just look at a so-called L2 framework, then even if your gap is just a constant, still you can only show its polynomial mixing. However, this amazing line of modified log Sobolev inequality will be able to further tighten the bound and show you there are cases, for example, if you have 1D commuting Hamiltonian, the gap is constant, and you can show using log Sobolev inequality that the mixing time is actually polylog. That is very significant.
Yeah,
Please.
One question. So when you say that there is no detailed balance condition, what do you mean by consider the symmetrization of?
I will show you an example later. Yeah, I will just say that, for example, if the whole Lindbladian is not detail balance, in other words, what is detail balance? It means you choose your favorite inner product. You want to check whether the Lindbladian is symmetric or self-adjoint under that inner product. If that's not the case, you can imagine I can take the Hermitian part, the self-adjoint part. I can still talk about that. I will give you a concrete example in the most minimized version to show you the idea of this so-called hypocoercivity.
That's to say the symmetrization may not always work.
Yeah, that's right. And that's why I will talk about the cases when symmetrization does not work. Okay, thank you for the remark. So I guess the takeaway for the previous work is to say that it's very important we want to estimate the spectral gap. Also, detail balance, as you can see, is extremely important. It's pretty much the beginning point of all of the consideration. So now what I want to say a little bit is actually estimating the spectral gap is a very, very difficult task in reality, as many of us know. That's why we are attending this workshop. So just give you some simple examples. For example, even if my Hamiltonian part and dissipative part are utterly are super simple. For example, maybe my Hamiltonian part is just a transverse easy model, 1D, and you pretty much know everything. And your noise maybe just some simple poly noise, and then you pretty much know everything as well. However, as soon as you add them together, you want to say, okay, let's try to estimate the spectral gap. That's actually not as simple as a problem to treat both of them separately. Another scenario you can imagine is suppose my dissipative part have a bunch of jump rate operators. Maybe they only acting on very few size that I'm considering. And then I put it in a super large Hilbert space where H acting on all of these terms. So if you only look at the dissipative part, there are many things you can do with it. However, as soon as you put it into a super large Hilbert space, the whole spectral gap estimation is going to become difficult. So the corresponding question that I want to address in this talk is that, is it possible, suppose I do have very simple D and I have very simple Hamiltonian, is it possible to have some way, or at least the existence maybe of some sufficient conditions so that I can treat the D part and H part separately, somewhat separately, you will see what I mean later, yet still yield a mixing time estimation. And also we want to ask ourselves, does detail balance have to be the beginning point? So what if my Lindbladian as a whole do not satisfy detail balance at the very beginning? Can you say at least there exists, some Lindblad equation, although detail balance is not satisfied, yet you can still say a little bit something about the mixing time. So that's what I'm going to discuss now. So regarding this question, I would say the answer is yes, because I'm only asking, is there any cases? So there are cases. So concretely, in this work, we propose a theoretical framework where we propose a set of sufficient conditions, if you like, where we treat this H and D sort of in a somewhat separate fashion. I will show you what the conditions are. And then we can still establish this exponential convergence of the Lindbladian equation to its equilibrium. And the second thing is that throughout our discussion later, we will not assume the whole Lindbladian have a detail balance to begin with. And I'm not saying in all the cases where I can treat it, that definitely not. But there exists at least some cases where Lindbladian is not detail balanced. Nevertheless, we can prove a convergent ring. So you may wonder, okay, fine, you have a theoretical framework. So what? Mathematically, you can do whatever you like. You can define whatever condition you like, and you can prove beautiful theorems about it, beautiful properties. But if there's absolutely no applications, then maybe that's not as interesting. So I will indeed show some applications, which may be interesting to you, may not be interesting to you. But what I will show is I will consider some simple polynoise, and I will show you the following 3 examples. One is transverse field easy model, Heisenberg model, and quantum work where we can provide, well, for these models, the conditions that we want to satisfy can be very easily checked. And lastly, I just want to say that the construction of this is really the dynamical system viewpoint, where we want to come up with the optimal functional. And how to come up with that is tightly associated and inspired by the concept of hypercoercivity, which originates from the kinetic theory. So before I dive into our result, I will just first talk a little bit of what exactly is hypercoercivity. So here is some history slides to respect all of these geniuses who come up with the idea. So hypercoercivity is originally proposed to study the so-called kinetic theory. It means the theory for kinetic equation. So what are kinetic equations? We are all familiar with the Schrodinger equation, which are on the quantum level, fundamental level. And then if say there is an object, I give it some force, then this is a dynamical system level, which is classical dynamics. And then we also know if we want to send a plane to the sky, it's the fluid dynamics. So the kinetic equation is actually in between these two levels. Specifically, if we talk about the rarefied gas or plasma, then those equations are kinetic equations. Some famous example includes Boltzmann equation, Fokker-Planck's equation, Wolff-Boson equation, and so on and so forth. So the hypercoercivity was originally proposed to study this type of equations by the famous mathematician Villani back into 2001 and 2005, where at the time he didn't name it hypercoercivity. And later he wrote it into a memoir and then later published as a sort of a book and formally named it as a hypercoercivity. And Villani was awarded a Fields Medal due to his contribution to kinetic equations. One is precisely the equilibrium behavior, hypercoercivity. The other was the Landau damping, which is also a kinetic equation relevant object. So there's indeed, after that, as you can see, this is a really significant involvement in the mathematical side. After that, there are many famous and great mathematicians come into the play, and they have developed different frameworks and made significant advances into the hypercoercivity field. So some of the notable example is, for example, Moholt was one of the students by Villani. He, together with Villani, also write the other work, Landau damping, that leads to Villani's Fields Medal. And Moholt, together with Dubout and Schmeisser, they further developed a very significant framework of hypercoercivity, which further inspired many of the later applications. And also, just to talk about the application, originates from the kinetic theory. As you can imagine, previously I have these slides where all of the physical dynamics are actually tightly connected. So you can imagine the hypercoercivity, if you go to the other side of limit, where you have some fluid dynamics, where people have, such as Jacob Bertelsen and so on, their collaborators and A.V. Sofer, they have shown that hypercoercivity can also be used to study shear flows and some invasive damping behaviors that are significant. And on the other side, the dynamical system side, since kinetic equation is closely tied by dynamical system SDE, which is further tied to sampling problems, and we have the expert Jian Feng, who developed a lot of frameworks and hypercoercivity related results over there for sampling applications. And also there's mathematical biology, such as blockings and uncertainty quantification, and so on and so forth. There are just many more applications. So today, I'm very glad to present that we also have a quantum application. So in terms of my previous graph, we can say now hypercoercivity complete the whole picture. So quantum, we can also use hypercoercivity. Now I'm going to discuss in a minimal example, what exactly is hypercoercivity, please.
That's exactly what I was asking.
Yeah.
Sorry.
Right. So I wouldn't take the credit of this this simple ODE example to myself. It was actually dated back to Arnold, a talk that I attended back in 2017. At the time, I wasn't working on quantum computing. I was still very much involved in the kinetic community. And he had this, I find, ingenious demonstration, very simple demonstration through ODE, what is hypercoercivity. So I decided to show you. So now I'm just going to consider a very simple ODE. Forget about Lindbladian, forget about quantum dynamics. And this is negative A, and where I'm going to talk about the coercivity. So you cannot talk about hypercoercivity without defining what is coercivity. So coercive is defined if the Hermitian part of any of the matrix we can always be decomposed into the Hermitian part and anti-Hermitian part. Coercivity states that if the Hermitian part has this bounds, then correspondingly you can immediately get a exponential decay. You can sort of imagine this is under the detail balance, and the spectral gap, we immediately get an exponential decay. But then the natural question that they have been asked is that is coercivity the necessary condition for you to get exponential decay? Certainly not, right? If we think about the simple ODEs, this slide is just to show you a little bit, how do I get the exponential decay? I think this is fairly important. So I just show you similar behavior happens in the Lindbladian case as well. So the way that you prove it is by energy functional methods, by the Lyapunov functional methods. So you want to take the inner product between the x and you look at what the differential equation, and you hope this is bounded by what I say, bounded by negative g and x norm, so that you can just simply do that, and you can substitute the e. Then what will happen is, please everyone think together with me for 3 seconds of what is the outcome of this product. Is you will, I should have counted 3 seconds. Is that you will get the Hermitian part. So that's why Hermitian part is coercivity that's related to exponential decay. So correspondingly, we get that. And here I just do the simple chain rule and so on and so forth. We get precisely the previous case. The question is then, is coercivity a necessary condition for exponential decay? Certainly not. It's because in simple ODEs, we have, simple ODEs are so simple, we can just write it into its Jordan form and so on and so forth. There was a question, please.
So in the previous slide, you had x, a, x, the a is equal to ah, but aa, so there should be a term aa, right? So where is the term aa go? I'm kind of confused.
You mean this term, or like from here to here? Is that the question?
Second, the third
from here to here?
Yeah,
it's because the Hermitian part is defined by 1/2 of a plus a dagger, and so that's precisely what this is. This corresponds to.
So a is equal to ah plus aa, right? So
the Hermitian part of a, I should have written it, is that it's 1/2 of a plus a dagger. And the anti-Hermitian part is the opposite.
So you say that that part is.
Yeah, that's right. So just to recall back, as what I will, you will see later, anything that is anti-Hermitian will just disappear in this energy estimation. So let me continue the story. If that's really the case, for all of the simple ODEs, we can just write it into the Jordan canonical form, and then we will immediately get this asymptotic behavior, which is what I teach in my ODE class last month. And so this is a very simple example. So what I'm trying to say is, through this very simple example, what is the Hermitian part is just the diagonal part. What you immediately realize is that, this needs to hold for all x. You can simply take the eigenvalues of the 0 mode, and you just plug in, you realize it's 0. So your G is going to just be 0. In other words, through this coercivity argument, you will not be able to get any of the decay. But the question is it really no decay? Well, the answer is certainly no. It's because we can look at the eigenvalues, which give us this. So by simple ODE basics, we know that this actually gave us a decay rate that is precisely 1/2. The way you do it is to think about the fundamental matrix where A is, T and Jordan block T inverse, and then you multiply both cases. I just want to make a quick comment why, say, you do not want to necessarily do it in that way in reality, even for later Lindbladian equation, is that if you do that way, you realize the symptotic behavior, the constant will have the norm of T and the T inverse, which is a condition number of a matrix, which can be arbitrarily bad. So still, even in these cases, the energy method is still going to be very helpful. That's why we do not ditch the energy method. Instead, we want to say, is there any modifications we can do to the energy methods so that we can yield something helpful? So this was just the previous plot where I'm plotting the derivative of the L2 norm, and the precise reason where I cannot get decays, because you can see there is a bunch of plateaus where the derivative is flat, so that I can just get something that is bounded by 0 instead of saying that is actually decay. If you think about from the level set viewpoint, x squared, y squared, this is our Lyapunov functional, you draw a bunch of the level set, what you will see is that the solution sometimes become tangential to each of the level sets, so you can no longer guarantee it is decaying to your equilibrium. So what is the easy fix? actually, the easy fix is just to say, well, instead of consider the regular L2 norm, which is the energy we typically use, we want to consider a twisted L2 norm. Precisely, the twisted L2 norm for this simple case is just that. So what will happen is you can treat it as the optimal functional, and then you just work out all the simple algebras. You will see it gives you precisely -1/2 rate as what is expected originally. So on this graph, I'm just showing that if you look at this new twisted norm, you can actually get exponential decay. There's no plateaus. And if you think about the level set picture, is this new level sets, and it will guarantee the solution will never, the direction of the solution will never become tangential to the level sets, to the optimal functions. So this is, I would claim that this is really the key idea of what is hypocoercivity. So in the simple ODE case, we can sort of define hypocoercivity in the case where A is not coercive, yet we can still have exponential decay. So,
is there a way to stare at this and come up with this P?
Come up with this. Yeah, that's right. So how to come up with the P is the part of the proof. That's what we are supposed to figure out ourselves. That's a very good question. So for this simple the optimal functional case, it's very simple to come up with the P. It's for ODE case, it's pretty simple to come up with it.
How?
Oh, you just put the P11, P12, and you just calculate it, and you want to that's actually this is when I teach ODE, this is one of the homework questions. That for this it is easy.
Once you have the P, I agree. But how to come up with this particular P?
Oh no! What I want to say is that you write out all of these things. You write out all the right-hand side, and you want to control the right-hand side by some constant which you don't know yet, and together with the P norm. So you can write out. This is a simple 2x2 cases. You can write out the whole right-hand side, and you can write a constant C times the P norm, and you have all of the coefficients, and then you start to choose the P11, P12, all the 4 degrees of freedom, so that you can actually get that. Actually, for this case, it's 2 degrees of freedom because the off diagonals needs to be the same. So you can actually play around with that and get it.
Yes. So under the same setting,
yeah.
If I have a much more complicated matrix, then basically what I need to do is I first transform it to a Jordan form. Then for any Jordan form, you have a canonical way to come out with the P. And then you just plug that. So.
Yeah. That was sort of the way that I want to avoid, because once we go to the Jordan form, we have the transform matrix T, and we have the the condition number of the T. That's what I try to avoid.
It's all a semi-definite program.
That's true. Yeah. Thank you. Okay. So now I'm going to talk about the Lindbladian equation, bring our back to the quantum application. So I'm going to, please.
Is that you have proven the exponential decay in the P norm, but then in the end you have to do some interpolation to get okay.
Yeah, it's very important. That's a good question. It's very important that in the end you show that these two are actually equivalent. Yeah, thank you. So
Finite dimension, they're always equivalent.
Oh, that's right. That's right. Then the finite dimension is already equivalent, but we need to figure out like what's the constant. But usually, it's system side. Okay. For Lindbladian, I'm going to talk about the Heisenberg picture again, and just recall ourselves. This is the Hamiltonian part. This is the dissipative part. And what I want to just say is that if we just took this simple form, look at the Heisenberg picture, then we can realize that identity is always a fixed point. And identity is full rank. And I'm just going to, because this is a linear equation, so I can just simply choose our favorite inner product, choose any of your favorite inner product. We're going to use JNS, you can choose your favorite one. And then, because this is the linear equation, so I can just subtract any observable with A, which is the projection up to the A. I talk about the difference or the fluctuation around the equilibrium. So I want to prove this fluctuation is exponential tending to 0. If that's true, and then I get the exponential estimate. Then the question is, let's imagine this is a Lindbladian equation. Great. What if we do a naive energy method, just as what we did before? Will that work? Well, the thing is that now I have this new inner product, and I do this energy estimate for the new inner product. Let's just, on top of that, simplify the situation even further. let's imagine, suppose sigma is actually maximum mixed state, then the inner product is the same as the Hilbert-Schmitz inner product that are simple to deal with, just to imagine. So we immediately realize that this part is the Hermitian part is actually, anti-self-adjoint in the Hermitian inner product. In other words, when you do the energy estimate, this part will disappear. You will only see B. So this was just a simple illustration telling you that, well, it's just not going to work. However, you can, concretely, you can imagine a scenario where suppose D is degenerate in the sense that it has many kernels. The kernel dimension is larger than 1. So in this case, D is actually degenerate. The energy methods will just tell you nothing, right? Because, well, there's nothing. So what we want to treat is precisely this scenario. We are not saying we can treat all the scenario, but is there a case, at least we can argue there's something going on. So here is a simple intuition of why there are some scenario it's going to work. I'm just going, this is not a proof, it's just intuition. I'm just going to look at my favorite, chautorization. I'm a chautor person. So I'm going to chautorize it into T and D. Let's imagine we are doing the following. So I'm going to say the kernel of D there are many, the kernel, the dimension is bigger than 1. And then the projection onto the kernel, I will denote as T. So any arbitrary A can be decomposed into the part inside of the kernel, the part that is outside of the kernel. And then let's imagine what happens if I acting on exponential D here. It's not going to move anything. You will get, if you have this part, you'll get exponential of D. Just imagine you do a Taylor expansion, then anything other than identity will disappear. So you will just, nothing is going to move. However, what D is essentially doing is a dissipative operator. So we essentially hope that maybe D, although does not move this part, maybe it's dissipative, anything that is outside of the kernel, that is perpendicular to the kernel. So hopefully it damps anything there. After that, let's imagine what happens if I have exponential of H. Then I'm going to only focus on this part because this part is going to be exponential damping already. What happens there is that we can do a simple Taylor expansion. And then what we will realize is, suppose in a very simple scenario, that suppose if PHP actually equal to 0, then this is actually, the T is actually doing a stir of your A, where it's pushing P of A into something that is to the orthogonal part, right? So this is actually very important, is because you are doing a stir, it's now going to the orthogonal part, then next step, D will decay it, and then you just keep doing it, you can imagine. This is a precise scenario where the whole thing will still converge exponentially. So the question for us will just be how precisely we formulate that. So before that, here is a picture we also included in our manuscript. It's just to say, suppose I have a kernel of D where it includes this line, it has many kernels. So the D part is dissipative, and the Hamiltonian part is like stirring it around. So for any thing that is inside of a kernel, after Hamiltonian, it was stirred outside. Once it's outside, then the D part will dissipative it. And then finally you converge to the global equilibrium. This is the idea. All right. Now a more concrete example, if I think my time is still okay, is that suppose I just take this very simple example. I just want to give you a more, I guess it's already intuitive enough, but more intuitive is that this kernel D will be something that is diagonal. And what H will do is actually turn the diagonal into the off diagonal. So in this case, you can easily check that PHP is actually equal to 0 because diagonal off diagonal is no longer diagonal, so it's equal to 0. So, and you can simply compute in this very simple case that D is decaying anything that is outside of its kernel, which is off diagonal part. So good. Now I'm going to talk about the precise result of ours. And I already verbally described to you what are the conditions I actually need. Here I'm just going to repeat them. So first of all, I want this D, it do not need to decay everything. I want it to decay anything that is not inside of the kernel of D. So that's why it's I minus P. If I do not have this term, this will be coercive. But if I do have this term, this is hypercoercive. And the second condition will be proposed to H, which says that I want H to stir the dynamics. This, the kernel of D should not be, equilibrium of H as well. Then nothing is moving. Then our previous intuition will just not work. So I do need H to stir what's going on inside of P. And then I do have this condition of PHP equal to 0, so which will on top of that make sure the 30 is a orthogonal direction of the kernel of D. And finally, there is just to make explicit of the mixing time, we do want to have concrete estimate of all of the constants. This is just a condition to talk about what precisely the constants will be. You can imagine for a concrete example, suppose I have a Hamiltonian, and then these are D and H are associated with the the system size. There will be polyN, which you will see some example later. Please type.
Turn out in practice to be easier to estimate condition 1 and the lambdas for condition 1 and condition 2.
Yeah. So for all the examples that I show you, it's very easy to estimate. Yeah. But the certain question exists: is there more interesting example that you can ask?
So if you assume any of the right values are that fundamental, can you consider some general that there's some like values and such have to
Yeah, that's a great question. That's the open question. Thank you. Okay, so here is the theory. Suppose all the fault conditions are okay, then we can get exponential decay, and we can explicitly calculate what are the C's, what are the lambda, because we do understand, the constants are important. That's what essentially gave us the mixing time. These slides is pretty, difficult to swallow, but the point is that the mixing time estimate will have something look like this. This is due to duality. Our original show the Heisenberg picture is decaying exponentially, just a duality argument will get us here. And you can see the CM square, which I said CM is associated with the system size, which we'll see some concrete example later. And this is the format of what we have, please. Sure.
Sorry, go back.
Oh.
Is condition 3 really necessary, or we can relax it?
That's so I have it here so that I know explicitly what to put inside of these constants. Yeah, because if we imagine we're just doing k-local Hamiltonian, everything is, we are not dealing with unbounded operator at this moment. So everything is going to be bounded. Condition 3 is just quantify like precisely a quantitative way what is the bound, so that I can tell you what precisely they are in this estimate.
3, not 4.
Oh, 3. Oh, sorry. 3. Oh, sorry. That's the we currently work with 3, and that's the open question. The first future work that is to relax that we are working on it. Okay. Right. You can imagine it shouldn't be necessary, right?
Sigma inverse.
Oh.
That's only the final step.
Yeah. That's only the duality argument. Has nothing to do with hypercoercivity itself. Yeah. To get here. Yeah, to get here. That's right. Okay, so just several remarks. First of all, I didn't assume the whole Lindbladian have detailed balance as in any of the conditions. Second, and you can see later example, they actually do not. And another thing is the take-home message is that if you have the right Hamiltonian, it actually can enhance this mixing. It's because the way that it's playing around. So now let me just show you some of the example. The first example is very simple. It's a qubit. And I'm just going to look at this Hamiltonian, look at this jump operators, which are not necessarily that interesting or physically exciting, but this is what we can look at. And then all of the conditions can be very easily analyzed. And particularly, you can see that the unique fixed point is this guy. And then you can just simply, it's very simple calculation to check all of our 3 conditions. And correspondingly, we can produce you a mixing time. So this is example number 1. Then the question would be, what about n-body Hamiltonians, n-body examples? So for these, I will show you 3 n-body examples as I promised you. So in this part, I will just look at a very simple polynoise, which is a dephasing noise. So we know that the dephasing noise, the kernels are spanned by the Z strings. And it's also very easy to check because it's polychannel, so you pretty much know everything. The D part is 2 gamma. And let's look at the transverse field Ising model. So, I have a condition of D, which I already checked. I have a condition of H. Okay, just work a little bit. I have a condition of CM, and then that's related with the system size. What about the condition 3, which is PHP, dated back to Lexing's question? Then let's imagine for this concrete example, the kernel is Z string. So I take a Z string, I want PHP equal to 0. I take something from the Z string and I commute with it. So Z will just disappear, and I commute with it become Y. So it's no longer inside of the kernel because it's not Z string. So you can easily check that condition here. So the conclusion is that you can easily check all of the conditions, and the mixing time will give you some polynomial mixing. This was as what I promised before, and this CM is associated with the system size. So similarly, you can also do it in the Heisenberg picture, and there are similar conditions we can check, which you can find in our manuscript. And now just to say a little bit about what about quantum work. And then here is another example where I just look at a deregular kinetic graph, where I say that, okay, the graph have a spectral gap, which is delta. And then we can we look at the simple dephasing noise. And again, this is another example where all the conditions can be very easily checked. And in the end, you also have polynomial mixing. So I'm not saying all, I mean, these are, well, I'm just trying to construct to you some of the interesting examples to show you that this framework actually works. Oh, the sigma in this particular case is actually maximum mixed state. So that's not very exciting, but these are some examples where we can show the exponential decay rate. So now just to say a little bit about the proving ideas. The proving idea is actually, you can already tell from the simple ODE case, is that recall we said, okay, I want to do an energy estimate methods. And once we do the regular energy estimation methods, the symmetric part, well, the anti-self-adjoint part will disappear. You will just not see its contribution. Then well, it just will not work. So the idea will just be, we want to work with a twisted norm. So how to come up with a twisted norm? So the point is, we can come up with a twisted norm, which is defined in the following way, where this curly A is auxiliary operators where we can define, and there's some expression of it. You just work with it, you can prove everything. And the point is, this new twisted norm is actually equivalent to the original norm. So that's dated back to Lin's question. If I have a P norm and I can make it equivalent. Thank you. And in fact, inside of this estimate, you will realize condition 4 is not exactly in that form. All we need is in this form. But since we can show that curly A is a bounded operator, you can just replace it with this as a simpler form. But this is more relaxed condition. If you can check that, that will also be great. So I guess I can conclude. So today I talk about the framework to estimating mixing time of the Lindbladian system, which we treated H and D sort of in a separate fashion. But we do need to check, PHP equal to 0, which tell you some of the correlation between the two. And then it do not need to have a spectral gap of the full Lindbladian, which is typical the starting point. And we do not require it to have a detail balance. And so the open questions which was asked is, can we relax the condition PHP equal to 0? That's what we are working on. And then there are various different frameworks. As I said, hypercoercivity is this really rich mathematical field. There are so many geniuses has been working on it. There are various different opportunities, as I believe, that we can look at and see whether there's any quantum applications, quantum analog into. And this is a reference. And finally, let me just advertise, Duke, I believe Duke Math, now we have a very specialized, a great concentration in quantum computing and quantum information. These three folks are the authors of this paper. We also have Robert Calderbank, who needs no introduction, and Harry Pfister, who organized the last semester's error correction long program assignments. So if you have any talent, students or maybe potential postdoc candidates, please consider send them to us. Thank you very much.
Cool. Thanks a lot, Dee, for an amazing talk. We've got time for some questions. Andresh.
For a nice talk. I wanted to ask if you have any examples where you can prove mixing time bounds for a Gibbs state at non-infinite temperatures.
That's a great question. We don't currently. I guess that's one of the reasons why we come to this conference. Hope to talk to you. Yeah.
Right. Thank you.
Yeah. Thank you.
Quick question: is that related to the PHP thing?
That I'm not sure. That I'm not sure. That I don't think so. That I don't think so.
Somewhat relatedly, I want to ask, are there any explicit examples where it's hard to estimate the gap of the Lindbladian, but it's easy to estimate the mixing time using your method?
All the example I gave you.
Oh, there are. Okay.
Yeah.
Cool.
Any other questions? Okay, if not, I've got one question. So I'm kind of curious, does all of this transfer over straightforwardly to the case where you have time dependence or
question.
even more interestingly, stochastic terms?
Yeah, great question. So for time dependence, we can still cook up the Abnormal functional. But I want to say for time dependence problem, the spectral gap is really not going to tell us anything about the actual dynamics. If we just think about very simple ODE, we can cook up example, 2 by 2, diagonal is -1, -1, off diagonal, let's say e to the t, and then the spectrum is all decaying, but you can simply solve this differential equation, which tell you there is some unstable exponential growing mode. So generally, spectral gap is not going to be a relevant concept to think about general time dependent case. But if you can prove energy methods still work, that's you can still do something about it. Thank you, Lisa.
All right, any other further questions?
How sharp is this technique for hypocoercivity compared to other proofs techniques for hypocoercivity for spectral gap?
You mean how sharp? Well,
I mean, I know Jeff has worked on like time space.
Yeah. So yeah, you will hear about it tomorrow. Yeah. Okay.
But I mean, maybe which method will give you better confidence? I don't.
Yeah, actually, so I think what you will hear from Jianfang and Bowen's work tomorrow is that suppose I have alpha in front of my Hamiltonian part and I have gamma in front of my dissipative part. Then I ask myself, for example, what is the best alpha and gamma that I can tune so that the rate is better, but the conditions are same. Just that I can play around with finding the best, the Hamiltonian part so that it dissipates faster. That's they do have a work on it.
Yeah. Great. Yeah. How about you guys connect during the coffee break? So thank Dee one more time.
Thank you.
We have a 15-minute coffee break, and then be back in for the next talk.